Okay, this is our first instrumental analysis technique. It's spectroscopy. The word spectroscopy, the scope means like microscope, telescope, to look at something. Microscopy means the study, so the Y means the study. So we're looking at things and we're studying them. And the spectro means spectrum, like a range, so from short to tall. So the spectrum that we're looking at, the range that we're looking at, is the light, range of light. So we're looking at molecules, we're studying molecules by using the light spectrum. And from the light spectrum, this particular type of spectroscopy that we're using infrared light. Okay, this is, pause this, have a look at the slides. If you've already done notes on infrared spectroscopy, then you could start at slide 18 and start looking at the particular molecules. Okay, so take some notes. We need to know what qualitative and quantitative mean. Qualitative is using light to work out which chemicals, and we'll be using other techniques to work out which chemicals, and quantitative is to look at how much of a chemical that we're using. So we're doing all of these instrumental techniques. Infrared's the first one. So the first four tell you what particular chemical, and it's like forensic science, you know, what's the molecule. These two, chromatography and volumetric, will tell you how much of a particular chemical we've got. So spectroscopy, as I've said, is looking at using light to study molecules. In year 11 we looked at visible light and ultraviolet light to work out how much of a chemical we've got. This range of light, it's from long wavelengths up to short wavelengths. So these ultraviolet X-rays and gamma rays are really short wavelengths, so they have a lot of energy. These ones on this side of the visible range are long wavelengths and they have less energy. So for year 12, we're going to be looking at infrared and radio waves. In year 11, the high energy light made electrons jump to the next shell. Infrared and radio waves are low energy, so infrared makes the whole molecule vibrate, and radio waves only affect the protons and neutrons and they change their spin. So these two techniques are going to be used to look at what chemical we've got. Spectroscopy looks at making the whole molecule vibrate, so infrared light. These are two atoms with a covalent bond between them. If you give them the right type of light, then they will absorb that particular wavelength and it will make them vibrate more strongly. So all of these different bonds are affected by whether they're double bonds or triple bonds, the strength of the bond, and will also the type of light that you will need will also change depending on how big the atoms are. So the strength of the bonds, double bonds, triple bonds, and the size of the atoms affect the amount of light that you need. So if you have a particular type of bond, you need a particular type of infrared light that it can absorb that particular wavelength, and that will make it vibrate more. Okay, so take some notes. Infrared is qualitative. It's used to work out what the molecule is. It's used for molecules. Infrared is lower in energy than visible and UV light. It doesn't promote electrons to higher energy levels. The energy is used in the vibration of the molecule, the bending and stretching of the bonds. Most molecules will absorb infrared radiation, except symmetrical molecules like nitrogen or oxygen. Okay, these are notes in your book about what happens, so the bending of bonds, twisting, stretching, the movement. Okay, x-axis, so we're going to have a graph. The spectrums are similar to UV vis, except that the absorbency is not drawn. So we don't
put on the y-axis how much light is absorbed, we put how much light is actually transferred. The x-axis is the type of light used. It's not identified by its wavelength, so how long the wavelength is, but by 1 divided by the wavelength, which is called the wave number. So a way of working out whether you've got an infrared graph is by looking at the x-axis and the y-axis. Do you see these things written there? Wave number, as the wavelength gets shorter, 1 divided into that makes the wave number larger. So short wavelengths have a lot of energy, and a large wave number has a lot of energy. If you read this, 1 divided by centimeters, it's you can read it as the wave number is literally the number of waves that you would have every centimeter. Alright, so this is what they look like. Wave number on the bottom. So the x-axis is the wave number, which is 1 divided by, the larger the wave number, the shorter the wavelength. So up here we have short wavelengths and high energy. The y-axis is the transmittance of light, so how much light is allowed through. So from here to here, a lot of light has been transmitted, which means this gap here is the light that was absorbed. So you can see that the peaks are upside down. So all of this from here to here, this light was absorbed and that light was transmitted. So these are upside down peaks of absorbance of light. So which bonds absorb more energy? Strong bonds like triple bonds or weaker single bonds? So strong triple bonds absorb more energy, so you would need a higher frequency to make those bond move. Which bonds absorb more energy? A carbon bonded to a lighter atom like hydrogen or a heavy atom like bromine? This seems counterintuitive. It's the lighter one. They can move around more freely. So lighter atoms absorb more energy and would have peaks up in the high energy area. So if you look in your notes, you can find these. So the bonds that we're talking about, the functional group bonds, are the ones that we're interested in. So the hydroxyl, the carboxyl, which is actually made up of a carbonyl and hydroxyl groups, the amine groups, and so these three, hydroxyl, carboxyl, and amine, are the main ones that we're looking at. So you need to look in your data booklet at the type of bonds and the wave numbers that where the frequency of light, the wavelengths, it's being absorbed. You notice that there are quite a lot of carbonyl groups. There's 1, 2, 3, 4, 5 carbonyl groups. So depending on the situation, what's going on around them, they all absorb at slightly different wave numbers. And there's 2 hydroxyl groups, acids and alcohols, and they absorb at slightly different wave numbers as well. So when we look at our spectrums, anything above 1400, the wave number of 1400, is due to a functional group. Anything below is in an area called the fingerprint region. So it's not due to a particular functional group that we're able to identify. Alright, if we look at our wave number on the bottom here, you can see that it's not a linear, this is going up in 500, 500, 500, and then all of a sudden it's 1,000 and 1,000. So be really careful when you read these graphs, the jumps. And when we refer to our peaks, when we write about them, a peak that has a lot of absorbance is called a strong peak,
A peak that absorbs over a large range of wave number, a large band of wave numbers, is considered a broad peak. A narrow peak could be called a sharp peak as well. So when you're referring to a peak, you have to quote the specific range of wave numbers, the band that they would be at. Be really careful because there's multiple that you pick the correct one. Okay, so now we'll look at our functional groups. We've got alcohols. All alcohols have a distinct hydroxyl band. So this is a band of wave numbers between 3,200 and 3,600 centimeters to the -1. So the scale down here is not really very clear, but between 2,000, 3,000, so it's between 3,200 and 3,600. So this broad, strong peak is due to the hydroxyl group. So you must quote the full range when referring to the peak. And you also, if you're actually ever asked to write on the spectrum, you actually have to say that it's a hydroxyl peak due to an alcohol, because we can have hydroxyl peaks in a carboxylic acid as well, but they have a different range. For an alcohol, you also have the carbon is bonded to the oxygen, which is then bonded to the hydrogen. So you also have this group, which is around 1,000. The thing is, this is below 1,400, so this is in the fingerprint region. So it's really hard to identify which particular peaks are due to this one. This is a spectrum of ethanol. So how would you, this is the spectrum again, if you're asked to write on an exam that evidence to say what type of molecule this spectrum is due to, if you're asked to provide two pieces of evidence, you can say this is an IR spectrum due to an alcohol because it has a broad peak, between 3,200 and 3,600, which could be due to the hydroxyl group in an alcohol. And you'll get used to seeing this large peak here and getting used to the fact that it's a hydroxyl group. If you're asked for two bits of evidence, the other bit of evidence could be that there is no sharp peak, and we're going to look at this second peak here. No sharp peak around 1700, so between 1680 and 1740, which would be due to a carbonyl group, and we'll look at a carboxyl acid in a minute. So we're missing this peak around 1700. Okay, so these are two alcohols. This is 2-methylpropanol and ethanol. Okay, and they both have this broad peak between 3,200 and 3,550. They also here, this peak here is due to the carbon bonded to a hydrogen peak. So if you look in your data booklet, you can see these peak wave numbers. This is present on all hydrocarbons. Every single hydrocarbon has a carbon bonded to a hydrogen. So you get around 3,000 this peak here, and it can kind of help you work out this hydroxyl peak is just above it. Okay, and that other one around 100 is hard to find. It's hard to find here. These are two different alcohols. They both have the hydroxyl group, the broad peak, but in their fingerprint region, they've got a whole lot of different bands because of all of the other bonds that they have. Okay, so the fingerprint, they have a fingerprint to help identify the differences between them. So if this below 1400 is different, then they're different alcohols. Okay, this is our carboxylic acid. So you need to know the formula whenever you most of the time you're trying to identify, and you'll be given the molecular formula and you'll have to try and work out what particular chemical it is. So ethanoic acid, that's our semi-structural formula and our structural formula. So you see carboxylic acids have the hydroxyl group, but they also have this carbonyl group. And the carbonyl group has a peak around 1700. The hydroxyl group is different. The OH, that broad OH peak, it's further down, and it has run into the CH peak. So it's become one large peak. If you had to label it, make sure that you're very careful that you label. You could write this right over the peak, OH acid. But you have to say, you can't just write OH, because there's a hydroxyl group in a carboxylic acid, and there's a hydroxyl group in an alcohol. So you have to identify, is it an OH for an acid or is it an OH for an alcohol? And then this is our carbonyl peak, which is quite distinct, and it's around 1700. Okay, so that's exactly the same as what I showed you before. If you have to answer this question and provide two pieces of evidence, you would say that there's a broad peak between 2500 and 3500. So look up these numbers for the hydroxyl peak for a carboxylic acid. Make sure you get the right numbers. So it's due to a hydroxyl group in an acid. And note that it's lower and merges with the, you don't have to write that. Okay, and there's a sharp peak, so we would call this one a sharp peak or a narrow peak. So sharp peak. And it's around 1700, but you look it up and find the particular numbers. I should have centimeters to the -1 here, due to a carbonyl group in a carboxylic acid. Okay, so this carbonyl group you would also find in esters, aldehydes, or ketones. Okay, so what type of molecule is this spectrum due to? Provide two pieces of evidence. So the first thing that you could say, it's due to an ester, an aldehyde, or a ketone, as there is a sharp peak. I need to use the language at around 1700. Due to, so you're not really sure whether it's an ester, an aldehyde, or a ketone. You'd have to have some other sort of evidence to know which one of those it was, but you can see that it has a carbonyl group. And so because you're not sure which one, you don't have to quote the exact range. You can just say it's around 1700. You can also give evidence when you don't have peaks. So we have this, which you would also find in a carboxylic acid. So the fact that we don't have that great big peak here indicates that it's not a, there's no broad peak, so it doesn't have a hydroxyl group or an amine group. We'll look at them later. So it's not a carboxylic acid. Okay, so quite often with these you'll get a molecular formula, and you'll have to work out, what particular molecule is this when I've got 3 carbons, 6 hydrogens, and 2 oxygens. Both of these spectrums have the same formula, but different molecules. So these spectrums will help us work out what particular molecule we've got. So for this one, you can see we've got a sharp peak around 1700, so we've got the carbonyl peak, and we also have a broad peak around 3000. It's kind of merged with the CH peak, so this is indicating that we've got a carboxylic acid. So this particular spectrum, the 2 oxygens, one of them would be the carbonyl and the other one would be the hydroxyl in a carboxylic acid. This one here, we have a carbonyl, but we don't seem to have any other oxygen. So we could have 2 carbonyls, or we could have a carbon single bonded to an oxygen, which would be this peak here. You don't have to identify that. But this one was a carboxylic acid. It was propanoic acid, so it's got 3 carbons. And this one was an ester. So we've got our carbonyl, and then we've got a carbon bonded to an oxygen around the 1000. So you can see they both have 3 carbons, they both have 6 hydrogens, and they both have 2 oxygens. So the infrared spectrum has helped us decide between these 2 options. Okay, and you would need to be able to write and explain why you picked what you picked. So the top graph is due to propanoic acid because there's the broad peak in the band between 2500 and 3500. So you need to just look up your data booklet to get them due to the hydroxyl group in the acid. And it's missing in the second graph, and this second graph is due to the ester. Okay, amines and amides both have a nitrogen bonded to hydrogens. So the most characteristic band with an amine is a weak to medium band, so not a very big one. Somewhat broad, but not as broad as a hydroxyl group, around the same region. So you can see up here above the 3000, so we've got our distinctive carbon-hydrogen bond here, and then above it, instead of a great big hydroxyl group, we've got these twin peaks. So primary amines and amides. So when the amine group is on the end, that's a primary amine, you have 2 bonds, 2 hydrogens. And each of these absorb at slightly different frequencies. So you get these twin peaks. So they're more likely to give you a primary amine and amide because they have the twin spikes. Then they're probably unlikely to give you a secondary amine or amide. So if we look at these, primary amine on the end's got 2 hydrogens, whereas the secondary, the nitrogen is attached to a carbon and a carbon, so it's got 2 bonds already, and the third bond is to 1 hydrogen, so you only get 1 peak. So amides are like esters. They've got a carbonyl group, and instead of what was an alcohol, then they would have an amine. So this is a primary amide with just ammonia being bonded, and this is a secondary where the amine was attached to a carbon group. So you've got the CONH. So these secondary amines or amides, you've only got 1 nitrogen with 1 hydrogen, so you only get a single bond. This one is starting to look a bit like a hydroxyl group, so they were unlikely to give you one unless, of course, they told you the formula. Yeah, they're unlikely to give you one of these, I think, because then if they gave you the formula, you'd have an oxygen in it. So you're more likely to get these twin peaks. And then you would know as soon as you see the twin peaks that you've got a nitrogen bonded to hydrogens. These ones, if you've got a amide, you would also have a band around 1700 for the carbonyl group. Okay, and just to compare again with if we go back to these, you can look at those ones with the amine and then have another look at an alcohol. You can see how different the hydroxyl group is. So this is secondary alcohol. This one is so like an alcohol, got a hydroxyl group, but it's an acid, so it's come, instead of being quite split from the CH group, it's moved further down and has blended with it. It's carboxylic acid, so you also have the carbonyl group. And this doesn't have the OH group, it's just got a carbonyl group, so it's either a ketone, an ester, or an aldehyde.